thank you very much for joining us for our third seminar in this series. Richard and I are here representing the UK Multiple Long-Term Conditions Trials Collaborative, along with Andy Clegg, who's lurking in the background, and will join us towards the end for any questions. Just a few housekeeping things. So this is being recorded currently and will be available on YouTube. If you would keep your microphones muted and your videos off during the presentation, that would be great. Thank you. And yeah, I think without further ado, I'll hand over to Richard Riley, who, as it says there, is a Professor of Biostatistics at University of Birmingham, to give us a good grounding in this approach. Thanks very much, Richard.
No problem, Tom. Thanks so much for inviting me. So thanks for those that have joined to listen to this talk. So this is an introduction to individual participant data meta-analysis. It's not intended to be technical or statistical. It's just an overall view of the field and why I think it's a very good thing to be thinking about doing. So let's crack on. So throughout this talk, I'm going to explain the rationale for doing an IPD meta-analysis, the key steps that are involved. I will talk about statistical methods for IPD meta-analysis, not in too much technical detail, but just some of the broader ways of doing it. I'll particularly focus a lot on notable examples. So about halfway through the talk, I'll start to just litter this with real examples where IPD meta-analysis has made a big difference. But I'll also finish with some notes of caution. And this is really for, Tom mentioned multiple long-term conditions, but this is really for any field where you could be applying an IPD meta-analysis to. So this is very broad. I'll talk a lot about treatment effects, but this could also be relevant for diagnostic tests, prediction models, and we'll have some examples of those as well. Also, I will add in some relevant, to some extent, football commentary quotes, just for fun to keep things interesting and to keep you awake. So here's the first one. Michael Owen, when he was commentating, said, "When they don't score, they hardly ever win." And what I intend to do today is to help you score when you're doing an IPD meta-analysis project to ensure that you do win, if that makes sense. Anyway, more quotes to come on that. So first part, rationale and key steps of an IPD meta-analysis project. So just to set the scene, in case you don't understand, but I'm sure you do, what is a meta-analysis? This is an example of a meta-analysis of 10 hypertension trials looking to see whether antihypertensive drugs reduce blood pressure. And I've got 10 trials in my meta-analysis. I've got the mean difference in blood pressure for those that are treated compared to control. So negative values are good because that means on average in that trial, there's a reduction in blood pressure for those treated compared to not treated. And in a meta-analysis, I do a weighted average across those 10 studies, and I get this overall pooled result here, giving me an overall treatment effect of about -10. So compared to placebo, there's about 10 millimeters of mercury reduction in blood pressure. And that's highly statistically significant. So that's a meta-analysis. In a standard meta-analysis, you would extract these estimates from each study from publications. But what I'm talking about today is an individual participant data approach where we get the raw data and we derive these estimates ourselves with the raw data. So IPD meta-analysis. IPD means individual participant data. Historically, if you look back, people would have called it individual patient data, but participant is a more inclusive word. And we're talking about the raw individual level data from primary studies identified by the review. So if you like, can think of it as the original source material. So any result that was published in a study article has been derived from the original source material, which is the IPD. So formally, an IPD meta-analysis is the synthesis of the IPD from multiple studies for the purposes of summarizing the evidence. This is increasingly relevant when we want to think about individualized evidence for decision making. So we may know this as stratified medicine or precision medicine, personalized medicine. And there's been a big call for IPD meta-analysis over the last 20 to 30 years. When we wrote our book a few years ago, I did a crude search of IPD meta-analysis articles, and you can see that in the last 10 or 15 years, this has increased quite dramatically. We're getting about 300 IPD meta-analysis articles a year now. And this correlates well with the fact that essentially data is becoming more available to us and the approach is becoming more feasible. Just in case you don't quite understand still, this is an excerpt of IPD from the 10 hypertensive trials that we introduced earlier. So when I've got my IPD and I've harmonized it and put it into a big database, this is what it would look like. So I'd have a row for every participant in every single trial. And for every participant, I would know what trial they were in. I'd know their ID. I'd know which treatment group they were allocated to, their age, their blood pressure at randomization, their blood pressure at 1 year, and so forth. Lots of information at the individual level. And I would have thousands of rows. 1,000 rows here for study 1, 300 for study 2, 4,000 for study 10, and so forth. So a massive data set. Crucially, this is at the individual level and not the study meta-analysis level. If you were to think about IPD from a cohort study, maybe let's just focus on cancer prognosis studies, this is the sort of thing you would see. Again, you'd have a row for every individual in the data set with a study identification number, and you would have biomarker levels for that individual. You'd have adjustment factors or prognostic factors for that individual, and you would have individual level information about their time of recurrence of disease, if they had it, their final survival time, almost their length of follow-up, and whether they were alive or dead at the end of follow-up. So individual level information, whereas in a standard meta-analysis, what you'd extract from each study would be the average age, the proportion of people that had an event, and so forth. So because we've got the raw data, we have many potential advantages compared to if we did a traditional meta-analysis where we extract study results, also known as aggregate data from publications. Let's go through some of these quickly. So first of all, because you got the raw data, you could maybe use more consistent inclusion and exclusion criteria across studies. So for example, if there were some studies which had children, you could remove those individuals if your focus was just in adults. Equally, maybe some individuals were excluded originally, you could reinstate them if that was appropriate. You can observe and account for missing data at the individual level, and we may be able to do that better than they originally done in the article. We can verify results that were published, so we can use the IPD to check if we get the same results as they did originally, and maybe that may raise some integrity issues or just give us more credibility in terms of the results that we're putting into the meta-analysis. We may be able to inform risk of bias assessments. We may even be able to reduce bias by doing analyses in a better way than they did originally. Come back onto that. We may be able to get up-to-date follow-up information. So maybe a study was published 5 years ago. You ask for their raw data, and they say, yeah, you can have this data, but also we have followed people up since the trial publication, and therefore we may get longer follow-up than the original publication. Of course, one of the big challenges with the standard meta-analysis is trying to get results from studies that we want. So if outcomes are not reported or summary statistics, for example, hazard ratios are not reported, we can derive them ourselves because we've got the raw data. So this may reduce problems of selective reporting within studies, for example, selective outcome reporting. When we do an IPD meta-analysis, we have to have lots of communication with the original authors, and it could be that during that process, they say to you, oh yeah, you can have the IPD for that trial that you want it for, but did you know we also did another trial which we didn't publish yet? And therefore, we could maybe start to get IPD and uncover trials that were not published, and therefore reduce the issue of publication bias that way. Because we got the IPD, we're in control. Now, this is what I really like as a statistician. I am in control of the analysis. I don't have to worry about how it was done originally because I can redo the analysis. So this means I can standardize my analysis strategy. So rather than dichotomizing continuous variables, I could model them on the continuous scale. I could therefore use more appropriate, more advanced statistical methods, and so forth. I can check modeling assumptions. So for example, in the Cox regression model, I could check whether the hazards are proportional, which is something that's important, but often not done in original publications. I may be wanting to adjust for prognostic factors. So in a trial, I may be wanting to get conditional treatment effects. And I can do that now because I've got the data and I can adjust for age, stage of disease, for example. This may reduce heterogeneity in my meta-analysis. I can, and this is crucial, I can obtain meta-analysis results much more easily for subgroups. So I can maybe look at males and females and see whether the treatment effect is different for males and females. This would therefore facilitate potentially calls for personalized and stratified medicine that I mentioned earlier. Moving away from trials, if I've got the raw data, I can examine and compare the accuracy of a diagnostic test using the same threshold for defining what's positive and negative in every single study. So I don't have to worry about people using different thresholds across studies. I can generate and validate prediction models. I could also account for correlation where needed. So, for example, sometimes we have studies where we have longitudinal data and we have individuals followed over time and we have multiple measures, for example, blood pressure at 6 months, 12 months, 24 months. I can account for that correlation properly if I've got the raw data. So lots and lots of potential advantages. Why is this feasible? Well, I think it's feasible because we are in an area where data sharing is becoming expected. So this is from a paper 10 years ago in the BMJ. And it just highlighted here that the Institute of Medicine joins many other organizations in making clear that study reporting and data sharing in medical research are imperative. And the questions ahead are how, not whether. And I think you'll have seen that in your own research. You know, if you get a trial funded nowadays, there is an expectation, sometimes it's mandated, that you will share your data upon reasonable request. Many people now put their data in a data sharing platform already. For example, look at things like the Yoda project. And data is becoming expected to be provided for projects like an IPD meta-analysis. But do you need to do an IPD meta-analysis? Clearly, in an ideal world, we'd all be doing an IPD meta-analysis, but they are a considerable undertaking, and sometimes a standard traditional meta-analysis and systematic review will suffice. So how do I decide? Well, really, the decision about whether you do an IPD meta-analysis is multifaceted. First of all, I would ask yourself, what am I interested in? What's the estimand? What's the measure of interest for your meta-analysis? If you're focused on the overall treatment effect averaged across everyone, then that's going to be less relevant for an IPD meta-analysis than if you were to be looking at subgroups or nonlinear complex relationships or developing individualized prediction models. So the more individualized you want to go in terms of your estimate, your estimand, the more nuanced, the more need for IPD. So, for example, overall treatment effects, you would expect them to be reported well in publications, maybe. But we should be able to get that information, whereas we wouldn't be able to get nonlinear relationships, subgroup effects, prediction modeling aspects from publications usually. Also, it depends on whether getting the IPD would improve the quality. So would it allow us to go beyond a study article in terms of understanding the study's risk of bias? Whether we would be able to adhere better to specific inclusion and exclusion criteria, checking modeling assumptions, including more outcomes, addressing selective reporting bias, like I said, maybe even standardizing variables in some way. So if we think getting the IPD would improve quality, then that may motivate it, even if we're still interested in the overall treatment effect. It also depends on the analysis methods in the original study. So if the original studies were all about time to event data and they used logistic regression and ignored issues of censoring, for example, they'd be worthless to me. But I could get the IPD and maybe I could analyze it in a much better way. So again, how have the original studies been analyzed? And indeed, how have they been reported? So they may have been analyzed well, but not reported well. We may be able to ask the study authors to get the results that we want. If not, we're going to need the IPD to address those reporting deficiencies. So think about the quality of the existing literature, how IPD may help you improve standards, and in particular, what it is in relation to the question you're trying to address. Okay, let me assume that you've decided to do an IPD meta-analysis project because you think it's going to be worthwhile. What are some of the steps that we need to go through? So, setup tasks. These are the steps that we need to take before essentially we get the IPD and start processing it. First of all, like any systematic review, we develop a project scope. What's the question? What are the estimands, the measures of interest statistically? Establish a central research team. So this is the people that are going to be doing the IPD meta-analysis projects. Later, we may get a collaborative team of people who involve the original study authors, but we always need there to be a central research team who have the ultimate responsibility for making decisions, for example, about what IPD should be included. You need to distinguish this team from collaborators who are providing IPD. We need to contact study investigators to get in principle agreement to collaborate. This may be important before you do a funding application, for example. We may look for other sources of IPD. So some IPD projects, for example, in Prognosis research, would get data that are routinely available, not just from studies, but from data sources. We need to develop data sharing agreements. So that's getting contracts in place to be able to provide for a collaborator to supply their data. We need to apply for research funding. This is not a quick undertaking, so getting funding to make sure the project is properly resourced is very important. And we may need to apply for ethical approval. Usually there'll be an exemption because you're using the original data in accordance with how it was originally meant to be analysed. Sorry, for the same sort of research questions, but that needs to be often checked. So there's a lot of things to think about in the setup phase. The central research team should include a broad range of researchers with experience from the method side, from obviously the clinical and healthcare side. People also experienced with collecting and harmonizing data. People who are good at communication with original authors, patient and public representatives, of course, too. All these projects still need to go through many of the same processes as a standard systematic review. One of those is to think about the research scope in terms of the PICOs or extensions like PICOTs, where we define the research question in relation to the PICOs. Now, a word of warning. Obtaining and harmonizing IPD can be quite a painful process. Those of you that have done IPD meta-analysis projects will know this. It often takes 12, maybe 24 months to get the IPD. Obviously, it depends on how many studies you want IPD from, but in reality, it's not a quick process. You need to persuade study authors. Like I said, you need to get data sharing agreements in place. We need to obtain the IPD and understand what the heck it is that they've sent us. You will get various formats of IPD sent to you, different rows which should be columns and columns with names which you don't understand. We need a data dictionary for each of the IPDs that we get sent. There can be a lot of back and forth with the original study authors, and they may get a bit cross about that because they may not have funds to support it. But you need to be polite and yeah, consistent with going back to them. We would need to check original publications to see if the information we're getting matches to some extent in terms of the number of participants in each group. You might want to check integrity of the trial. And there's a lovely IPD integrity tool by Kylie Hunter and colleagues that talk about how you use the IPD to check integrity of a study. For example, looking at randomization, whether the data may be fabricated and so forth. And ultimately, after all this process, we need to harmonize into a single merged data set. Thinking more about what data sharing agreements are like. So this is where my university has to agree with your university or place about how your data is transferred and how I'm going to use it, how I'm going to store it, whether there needs to be agreement on publications, loads and loads of back and forth. In fact, you can think of a data sharing agreement a bit like this. So I'm going to run that again because it's so funny. So basically, this is like my university trying to agree with your university about what the data sharing agreement would look like. And I wait for your university waits for my university, and it goes on and on. It can take many, many months and can be very frustrating. Not trying to put you off, but you need to recognize that. Okay. What about examining risk of bias? So risk of bias refers to the quality of a study. Now, a standard systematic review would base a risk of bias assessment on the information from a study in terms of the protocol, in terms of the study report, maybe also by information provided by study investigators. The good thing about an IPD meta-analysis is when you've got the IPD, you can enhance that risk of bias classification so it can be refined or updated based on the IPD itself. So some risk of bias concerns may be alleviated by actually having the IPD. So, for example, if they excluded individuals that they shouldn't have done, then you can reinstate them potentially. Conversely, you may find more risk of bias concerns than you originally thought about. So, for example, you may notice that there was strange baseline imbalances indicative potentially of flawed randomization only from looking at characteristics within the IPD that weren't reported in a table 1. Here's a real example from figure 4.9 in our book. So this is looking at the IPD in one trial. And what we were able to do once we got the IPD for this trial was to plot the randomization allocation. So what we can see is that we have the number randomized on the y-axis against the date, and the blue is one group and the red is another group. Now, clearly we can see that most of the first year, the blue group was the group that was randomized to, and then after that, it was mainly the red group. So clearly there's something's gone wrong here. This is not at random. What it is, we don't really know, but maybe there was an issue with the supply of the control group or the treatment group, which meant that they couldn't be given it until after a particular date. So this was revealed by the IPD and wouldn't have been known without the IPD. Okay, so we've got the IPD, we've cleaned it, we've got the data sharing agreements in place, we've checked the quality, and now we're thinking about meta-analysis. So we've got statistical methods for meta-analysis. So these potentially could be different from a standard meta-analysis, and I'll come on to this in a minute. We use a two-stage or a one-stage approach. I'll come back to that. As in any meta-analysis, we want to do a sensitivity analysis. So maybe we want to exclude trials at high risk of bias. Here, we potentially won't get IPD from all the studies that we wanted. So we may want to see if we can include some published results from non-IPD trials alongside the IPD from the trials we did get IPD from. We still may be interested in small study effects, publication bias related checks. After we've got our results, dissemination is important. So with an IPD meta-analysis, one of the advantages is that we should have incorporated this set of collaborators, and therefore disseminating our findings should be better, quicker, because we can engage those individuals, including patients and policymakers. In terms of reporting guidelines, there's PRISMA IPD. This is the main reporting guideline for IPD meta-analysis of trials. Also see tripod cluster for IPD meta-analysis of prediction models. Right, so I've been through sort of the rationale, the steps involved on a broad scale. I just want to narrow in on some specifics and then go into some examples. So, statistical approaches. Here's another football quote. And Wigan Athletic are certain to be promoted, barring a mathematical tragedy. So now I'm going to help you avoid mathematical tragedies for your statistical analysis of IPD meta-analysis. So in a two-stage approach to IPD meta-analysis, what we're doing is we're going to analyze our data in each study separately in the first stage, and then we're going to pull results in the second stage. So if we just focus on obtaining a pooled treatment effect estimate, then in the first stage, we would use a regression analysis probably to analyze the IPD in each study separately to derive the treatment effect estimate, the overall treatment effect estimate for that study. So that could be a mean difference or an odds ratio or a hazard ratio. In the second stage, we then take those study estimates of the treatment effects and pull those in a standard meta-analysis model. So a common effects or a random effects model. So the big difference here is that in a traditional meta-analysis, in step one, you would seek these estimates from study publications. Here, in an IPD meta-analysis in step one, I am deriving the study estimates myself using the IPD. There's a stata module called IPD Metan that does both these steps for you and produces nice plots and so forth. So do check out that. Thinking about that first stage in some more detail. So if it was a continuous outcome, I might use the linear regression. Binary outcome, a logistic regression. Time to event outcome, maybe a Cox regression. Obviously, that's a bit simplified, but that's the general thing that we would be thinking about using. And this leads to a treatment effect estimate. Here I denote it by theta I, and its variance v theta I. So I denotes a trial. And in the second stage, what I'm going to use is a standard meta-analysis model. So, for example, in a common effect or a fixed effect meta-analysis, I assume that all those treatment effect estimates across studies are some estimate of the underlying true treatment effect. But in a random effects meta-analysis, I assume that each study estimate is an estimate of the true value in that study, and then the true values across studies vary randomly about some average value according to some between study heterogeneity tau squared. That's as technical as I'm going to get in terms of the mathematics, but you're just using standard meta-analysis models in the second step. So let's go back to that hypertension trial meta-analysis I showed before. This was actually an IPD meta-analysis performed by Wang et al. And they got trials, 10 trials from the Indana dataset database and the Study Coordinating Centre in Leuven in Belgium. So these were IPDs that had been stored and they got those 10 datasets. 28,000 individuals in them. This was a sample of their data, again, truncated, of course, but we've got, as I showed earlier, patient ID, baseline blood pressure, final blood pressure, treatment group allocation, age of individuals, sex of individuals. So individual level information. So they kindly shared this data with me so I could redo and extend some of their analyses. So what would we do with this data? So in a two-stage analysis, in the first stage, I would use a analysis of covariance model. That's just statistical jargon for a linear regression where I adjust for baseline. And this allows me to obtain the treatment effect estimate in each trial, which is a mean difference in blood pressure at follow-up after adjusting for baseline. So let me apply ANCOVA to each of those 10 trials. I get my treatment effect estimates. Here for trial 1, it's minus 6.53, trial 2, minus 13.81, and so forth. I can also use the IPD to derive other summary information, such as the number of participants in each group, the average age, the mean blood pressure at baseline, and so forth. Then in the second stage, I'm going to use a random effects meta-analysis. I think there's likely to be heterogeneity in these trials, and therefore I'm going to allow for heterogeneity in a random effects meta-analysis model. So these are the meta-analysis results, and this is just what I showed you earlier, essentially. And I get my pooled meta-analysis result to be about minus 10, like I said earlier. strong evidence that antihypertensive treatment reduces blood pressure compared to control, as we would expect. Loss of heterogeneity to a square root of 3. We can see that in some studies, they're very different than other studies. But clearly, they're all below 0. So even though there's heterogeneity, there's strong evidence that it's likely to be beneficial everywhere. But let's pause for a minute. Was IPD actually needed here? What if every single trial was of good quality and that they used analysis of covariance? That they reported the treatment effect estimates in the paper with the variance or the 95% confidence interval? Then if I was only interested in the overall treatment effects, I didn't need the IPD because they were good quality trials, they were well reported, they used the right analysis methods, and I could have saved myself 2 years getting that data. So really carefully think about the quality of the existing trials and what it is you need before embarking on an IPD meta-analysis. However, of course, IPD meta-analyses are going to be needed in many situations. For example, when we want to go beyond the average treatment effect, or we need to think about improving analysis methods, obtaining outcomes that weren't properly reported, looking at subgroups, and so forth. But just a note of caution. There's an alternative to the two-stage meta-analysis approach, which is called a one-stage meta-analysis. This needs great care, and I wouldn't recommend most people did this unless you were statisticians and actually had experience of multi-level mixed effects modeling. So a one-stage analysis analyzes the IPD from all studies simultaneously. The reason why it needs great care is that we need to make sure that when we're fitting these models that we still account for clustering. Patients are nested within studies. We would break randomization if we forget that. So for example, we could use a multi-level regression model and allow for a separate intercept for each study. Usually, one-stage and two-stage approaches give very similar results, particularly if you're using the same estimation methods and making the same assumptions. But if you have most studies in the meta-analysis that have sparse numbers of participants or events, so for example, there are some studies which have 1 or 0 events for some outcomes, then the one-stage approach is going to be more exact and should be preferred. Tends to give results that have better statistical properties than the two-stage approach, for reasons which you can look into in this paper here. Two-stage or not two-stage, that is the question, if you want more details on that. Right, let's move on to some notable examples. Individualized prediction and other areas. So Paul Gascoigne, he said he never makes predictions and he never will. Obviously making a prediction when he says he will never make a prediction. But prediction and subgroup and all those individualized aspects is the key reason, I think, for doing an IPD meta-analysis a lot of the time. Like I said, this aligns with stratified or personalized medicine, going beyond the average treatment effect to look at how treatment or whatever it is you're looking at changes across individuals. Statistically, this means we want to estimate treatment covariate interactions. What is the difference in the treatment effect for one subgroup compared to another? So you may have heard of subgroup effects and effect modifiers in the same language, but it's really what we're focusing on is in an interaction and statistical sense. If you think about randomized trials, these are powered on the overall average treatment effects. They're not powered to detect individual level differences. And therefore, an IPD meta-analysis is really exciting to be able to increase power to detect genuine individual level interactions if they do exist. This is a really notable example from the 80s, 90s, 80s, where an IPD meta-analysis was used to identify that estrogen receptor status in breast cancer basically tells you whether to use tamoxifen or not. So clearly we see that those that are positive, the treatment is effective. Those that are negative, no clear evidence that it's effective. So this IPD meta-analysis result led to this interaction being found, which has strong biological rationale, and therefore tamoxifen has a direct indication in those that are positive. If we wanted to identify interactions and effect modifiers, then how would we do it? In a two-stage approach, we would estimate those interactions in each study separately. Then actually we would then pool those interactions in the second stage. In a one-stage approach, we can fit a regression model, again, properly specified with clustering and random effects, and include an interaction in that regression model. But again, be very careful here. You can't just put in an interaction term. You have to make sure there's separation between interactions at the individual level from associations at the study level. And I'll unpack this a little bit in the coming slides. But again, just a note of caution that it's very easy to get this wrong in a one-stage analysis. So what am I talking about here? So within study interactions means that I'm looking at the effect of individual covariates on treatment effect. So this is at the individual level. Think about explaining individual level variability. So the treatment effect for males compared to females is such and such. In a traditional meta-analysis where we would use a meta-regression, we don't have the IPD. What we tend to look at is how things change across studies. So this relates to across study interactions or associations. Basically, it's saying how does the average covariate value in a study, how is that associated with the average treatment effect? So it's an ecological level. So this is what meta-regression looks at. So for example, it would say, how does the overall treatment effect change across studies as the proportion of males changes across studies? So this explains and examines between study variability, but doesn't reflect patient level, individual level relationships necessarily. And this is a big warning. It's called ecological bias or confounding. We shouldn't be using meta-regression to examine individual level relationships. Let's go back to our data to illustrate this. So these were the 10 hypertension trials. And remember, this is the overall treatment effect result. So that's on average, but the question would still remain, does this treatment work equally well, let's say, for males and females? Well, if we wanted to look at that, we could examine, using the IPD, in a two-stage analysis, the difference, i.e. the interaction between males and females. So I've done that in each of these 10 studies, and I've got the difference in the treatment effect for males compared to females. And in most studies, if you look on average, it's very close to zero. And indeed, on average, it's 0.77. Not statistically significant, but even if it was, there's no real clinical difference in terms of a 0.77 millimeters of mercury difference in blood pressure in terms of a treatment effect. It's not relevant. So there's no evidence at the individual level that the treatment is less or more effective for males compared to females, which is good to know. Michael Owen, when he was commentating again, he said, that is a fantastic penalty, but he will be gutted it went wide. So what I don't want you to be doing is analyses that you think are fantastic, but actually you've actually missed. And this is what you would be doing if you did a meta-regression here. So remember, this is the result based on the IPD meta-analysis. I have shown that there's no significant effect. The effect is small. So thinking about this in real terms, if we thought the treatment effect reduced blood pressure by 20 millimeters of mercury in females, taking off 0.77, then for males, it would be 19.23 effect. So it's not significant, barely any difference. But if we looked across trials to see how the overall treatment effect changes as the proportion male changes across trials, we would find this interaction. 15, highly significant. This would lead us to think that actually there possibly is a difference between males and females. So essentially what this means is if your study only recruited females and that study had a treatment effect of 20, then a study that only recruited males would have a treatment effect of 4.98. Now that's very dramatic, but it's completely wrong. It doesn't reflect the individual level at all. There is no difference between males and females. And what's happening here is ecological bias, aggregation bias, confounding. If you didn't have the IPD, you wouldn't know this, and it could lead to some very wrong decisions being made. So what is going on here? Let's try and look at this from a graphical point of view. Here I'm plotting the overall treatment effect in a trial against the proportion male in that trial, and each of these squares denotes one of my trials. You can see from the meta-regression, the across-study relationship is very strong. As a proportion male in a trial increases, the average treatment effect gets closer to zero, so less effective. But the gradient of the dashed lines is what I looked at the individual level. So the difference between males and females is denoted by the gradient of these dashed lines, which in the bigger studies, the bigger squares, they're pretty flat. And indeed, the average of the dashed line gradients is 0.77. So what's happening here is confounding. So, for example, it could be that in those trials that had a higher proportion male, it also had a shorter length of follow-up or a lower dose. So it's only at the individual level that you start to really unpack individual differences, and hence why we want the IPD meta-analysis. Andrea Leadsom, this is not a football commentary, but it's still funny. I have never and will not start predicting the future. I don't do predictions ever. A few hours later, she said, I'm a very strong arch Brexiteer. I genuinely believe that we have a bright future ahead of us when we leave the EU. So she doesn't make predictions, but she's happy to predict the future. What other predictions can we think about in IPD meta-analysis? I'll just go through some very quick examples. First of all, is we can actually look at nonlinear relationships. So going back to that hypertension data, here I've got a nonlinear interaction between the effect of age and the effect of, the age and the effect of hypertensive treatment. So I've got a reference group of somebody aged 55. In those that are younger, the treatment doesn't seem to work as well. And after 55, there doesn't seem to be much difference compared to 55. So there's some strong evidence here that younger people, it's not as effective as in older people. But this is a nonlinear relationship of modeling on a continuous scale, the variable age, rather than if I didn't have IPD, what would people do? They'd probably dichotomize age of 60, 65, 70 or something. I couldn't do this. But again, you've got much more power to do something better. In terms of prediction modeling, I can do lots of really exciting things. So this is just one little bit I'm going to show you based on this paper here. Essentially, we can validate models in multiple settings. When I do this, I want to check if my model predictions are well calibrated. Franz Beckenbauer said, 1 year I played 15 months. Now that's an example of statistical information that's miscalibrated. Clearly, it can't play more than 15 months, but sometimes when we make predictions, for example, of risk, it may be too high or systematically too low. I got IPD from 8 countries and I validated a breast cancer prediction model. And what I'm looking for is a calibration slope of 1. And what I saw was huge heterogeneity across the countries. So in some countries, the calibration slope was much less than 1. Others, it was much bigger than 1. Interestingly, on average, it was 1 across the countries, but that's a statistical pointless summary result when actually in individual countries it was miscalibrated. What I want is for in every single country it to be well calibrated. You wouldn't be able to get and check this without IPD because it wouldn't be reported in publications for prediction models very well. But what I can also do is to say, okay, the models don't work, the model doesn't work well, but what if I was to recalibrate my model? So in prediction modeling, we can do that in many ways. One way is to update the model intercepts, a very simple tweak based on the local data. What if I did that? Now I see that the calibration slope estimates are pretty close to 1 in every single country. I still get my average of 1, but if I was to look across those countries, I would predict a very narrow range for the calibration slope, whereas before it was very, very wide. So very exciting that we can recalibrate and update prediction models. I can also look at added prognostic value. So one of the first IPD meta-analysis in the prognosis field was done by Maria-Elena Trivella, Doug Altman and colleagues. They got IPD from 17 studies, 3,000 participants to see whether microvesicle density was a prognostic factor for death. IPD enabled them to do lots of things that you wouldn't be able to do otherwise. So for example, it enabled them to disentangle different measurement methods. It allowed them to adjust for existing prognostic factors of age and stage of disease, and importantly, it allowed them to analyze MVD on its continuous scale. Their findings completely contradicted an earlier meta-analysis that was based on aggregate data. Now, that had suggested that MVD was hugely prognostic. When Travella and colleagues did it, and they did their IPD meta-analysis, This is what they found. Their summary result very close to 1. After adjusting for age and stage and being consistent in the measurement method, there's no difference. So there's no effect of MVD. So again, IPD meta-analysis, more robust, more reliable, getting different answers. Moving on to test accuracy, one of the big problems with test accuracy reports across studies is, as I said earlier, they use different thresholds. Now, that means that if we did a meta-analysis, for each threshold across studies, we would end up with an improper ROC curve. So this is denoted by the grey line here. This should be monotonically increasing, but because we've got different studies contributing to the curve, we get this strange phenomenon where it goes up and down. But with the IPD, we can make sure that every single threshold has the same number of studies, and we get this monotonically increasing ROC curve to base decisions about whether task accuracy is good at particular thresholds. Right, I'm coming to the end now, last few minutes. Just wanted to finish with a note of caution. So I've given you some really exciting examples where IPD meta-analysis could be useful, but they're not always the gold standard. We often use the word gold standard when we're referring to IPD meta-analysis, but like I say, there are challenges with the approach, not just in terms of the time it takes to do it, but also because there may be biases that you introduce along the way. So, for example, you may introduce biases in terms of the identification of relevant studies to collect IPD from. You may be selective in, even after you've identified all the studies, you may be selective in which studies you ask IPD from. Studies won't always give you the IPD, and therefore, is there some systematic bias in terms of which studies are giving you their IPD? I'd be more worried about studies that don't give you the IPD in terms of their quality, and so forth. So just to note, as Steve McLaren said, we have to reduce our expectations of England, and we have the players to do it. So when he was manager of England, he certainly did reduce our expectations of England. So just, I'm bigging up IPD meta-analysis, but we have to reduce our expectations sometimes. It's like any research method, it's not perfect. So costly, it's going to need data managers, advanced stats, specialist techniques, travel maybe to see collaborators, time consuming. Going back to that Travella prognostic factor meta-analysis, they reported checking validation and standardization of all data sets took nearly 2 years. And that's typically how long a project would take. Heterogeneity is still likely. Just because you've got the IPD doesn't mean that you're not going to have issues of heterogeneity. You'll have inconsistent variables in different studies, different types of coding and measurement methods, and so forth. So you won't be able to resolve all that problem. A study that's crap will still be crap after you got the IPD. So just because you got the IPD doesn't make it a good quality study. You may be able to improve quality in a little bit, but of course, if the randomization was awful, then you can't resolve that. Like I said, more advanced analysis methods will be required. So we need specialist statisticians. I think that's always a good thing, though. We may need to deal with missing data. Collecting IPD can be painful. Like I said, it's worth just looking at this quote as I come to an end. Why did it take 90 months to retrieve clinical trial data from a non-profit organization? In this paper, they say the emails we received during the prolonged exchange were all friendly and the individuals involved were helpful and understood the need for data sharing, but they were hampered by inflexible, formalistic, and slow bureaucratic procedures. Since our first inquiry, we communicated with 4 people, sent 25 emails, filled in 4 data use agreements, and waited for 1 year, 7 months. So that comes back to the that football video that I showed you earlier. So, in summary, IPD meta-analysis has notable and laudable advantages. I think I've emphasized that with the examples, really big impact examples. But they may not always be needed, and they need serious undertaking. They should be increasingly helpful in this era of data sharing and stratified medicine, allowing us to go beyond overall average effects and look at individualized results, the subgroup and treatment covariate interactions, individualized prediction, and so forth. Meta-analysis modeling, 1-stage or a 2-stage approach. 2-stage approach usually should be fine unless events are rare. And also don't automatically assume an IPD meta-analysis is the gold standard because issues may exist. If you want to learn more about IPD meta-analysis, I've set up this educational website, ipdma.co.uk. It's got some entry-level guidance and videos, code, training resources, and notes about courses. And like I mentioned, we published a book on this topic a few years ago. I hope that's been really useful, and we've got a bit of time now for questions. So I will pause there and hand you back to Tom. Thank you.
Thanks very much, Richard. That was absolutely fantastic. Really really helpful, really clear. Thank you. We've had some good questions already in the chat.
Okay.
Yeah, and I did enjoy your football quotes, um, particularly Gazza's, but yeah, lots of great ones in there. So Christina asked whether you need to do a power calculation for IPD meta-analysis, and I know you've got well, quite a lot of thoughts on this. So
Yeah, I think you do need to do a power calculation. At the minute, we don't have much guidance on this. There's a chapter in the book on this, but it mainly focuses on interactions. Um, it's a funny one because obviously we're not thinking of doing a new study, but what the power calculations are doing is saying, okay, we know that there are this number of studies that are willing to provide their IPD. So conditional on those studies and conditional on the information in those studies, such as the number of participants and events, and we should roughly know what that is based on publications, then under assumptions about what the true value is of, let's say, the interaction of interest, that we should be able to calculate the power of that IPD meta-analysis. If you were to know that your IPD meta-analysis had a 20% power, well, I think that's important because you might not do it then, and the funder may not fund you. If you were to be able to demonstrate that you had an 80, 90% power, then that gives more, gravitas to actually doing the project, I think. So yeah, if we can, I think you might be seeing a lot more from us in that area in the next few years.
thank you. There was a question from Sally Wheelwright about whether you'd offer authorship typically to someone from each team who provides a set of data.
Yeah, you probably would, because like I said, there was a lot of back and forth, so they are contributing. What I would say though is that this is probably best done as a collaborative group. So you'd have your core IPD meta-analysis research team as the main authors, but then you'd have the collaborative group as a named co-author, and then you would list that group with the names underneath. Now, usually PubMed would still pick those people up as authors, and that would come across. And it should be that they pick that up. But you would do it as a named collaborative group rather than actually naming 40 people in the author list per se. I think that's just a better compromise way of doing it. Because you do need to pick out the central research team from the people who've just supplied data.
Thank you. Yeah, Andy gave a similar reply, so that's good. Azada Abravan, I'm not sure whether I've pronounced your name right. There's a question about whether you'd recommend any platform where you can submit expressions of interest to identify or get in touch with institutions with similar interest in research questions for IPD meta-analysis. Not sure.
Oh, I don't know that specifically. I think it's always context specific. So usually it's about getting in touch with the study investigators directly, and trying to get some momentum that way. It always helps to try and get leaders in the field, whoever they are, or however you would define that, to be involved in your projects, because that just gives extra weight. Because if you go to people and say, look, we've got these leaders in the field involved, would you therefore also want to be involved? I think it helps them. Some database is though, for example, the like the Yoda project, you don't need permission, you can just apply for it, as such. Yeah.
Thank you. Uh, Christina also asked whether there's any ways to account for confounding if you were undertaking a meta-regression.
So if you don't have the IPD, no, basically. So if you were to look at this is looking at patient level characteristics that are aggregated, you don't know. You just don't know. So there's no way to address that without the IPD. The worry though is that even when you've got the IPD, that confounding can still influence the results if you don't analyze it properly. So I talked about the two-stage approach, and that pools interactions in each study, so that always avoids it. But if you to do a one-stage model, if you just put in the interaction term, what that does is it amalgamates the within study relationship with the across study relationship. And so you get a weighted average in some way of the two. So the across study relationship can still confound and distort the within study relationship in a one stage model unless you separate those two things out. And you can separate them out by centering covariate values by the means in each trial. Um, and other technical ways, which I won't go into now. But yeah, you need the IPD to do this properly.
Thanks very much. Let's see. Sarah Compton, I've been using a one-stage IPDMA to pull the data from a randomized controlled pilot and main trial. Is this an appropriate use of the method?
Yes, but again, those two pilot and main trials, I would allow clustering within that situation. So you would not just put in one regression model and treat it like one big trial. You would have separate intercepts for each trial, at least, and maybe allow for a random effect on the treatment effect. But with it being a pilot and a main trial, maybe sounds like it might be from the same population and same center. Maybe there won't be a lot of issues anyway in terms of heterogeneity there.
Uh, Comment different sites. There are different sites. So
Okay, yeah. Yeah. So a proper IPD meta-analysis, yeah.
great. Thank you. Um, Darren's asked if you can't get IPD from all the identified studies, at what point do you call it a day and say aggregated meta-analysis is going to be better?
Completely depends on the research question. So, for example, if you were to look at interactions, even if you could only get IPD from, let's say, 10–20% of the studies, you probably can still do a lot more with those than you could do with the aggregate data from published studies because the interactions are just not going to be available. So yeah, it completely depends on the question. Obviously, then wondering about whether that's a selective set of studies. But often what we do is we go beyond the original questions that were looked at in the original studies, and therefore we're going to get new information. So it's not like those other studies know there's no interaction and therefore don't want to give it to you. They often just don't know. So I think IPD meta-analysis can be beneficial even with only a small bits of studies giving you their IPD if it's going beyond and looking at something new. And if those studies were representative of your target population. So it really depends on the question, I think.
Thank you. Yeah, I suppose the maybe the other part of that is that if you're doing a two-stage analysis and it is something that could be answered with the aggregate data, that you can combine the two approaches.
Yes, yeah, yeah, that's a good point. Yeah, yeah.
Um, and we've where we're 12:59, so people may need to leave. I don't know how you are for time, Richard.
Yeah, I'm okay, 5 more minutes.
Great. So what is your views or suggestions on reproducibility of IPDMA?
I think that's exactly the same as it should be for any project. So again, we should be making protocols and transparently reporting our methodology. And again, ideally, that IPD meta-analysis data set should be available. Again, you have trouble with that because that's not yours, and it's got components from original people. One way of maybe helping address that is by setting up a repository in particular disease fields, where the IPD meta-analysis data set is stored in this repository so that other people can access it, to check your results, but also to do additional analyses. And then when new trials and studies are done in that same field, they enter it into that same disease field specific repository. That'd be nice. I really worry that a lot of IPD meta-analysis time is lost because basically people are not storing their data afterwards. So people have to who want to do it, they have to do it all again, which is that is just ridiculous. So it'd be nice if people were building on previous IPD meta-analysis.
Thank you. Yeah, and that's some of the work that Andy and I are starting to do around aging trials. Um, this question: does the number of studies in IPD analysis influence the choice of a one-step versus two steps? For example, the assumption of normality of the distribution of the study effects in the two-step method.
That's a good question. I don't think so. I don't think it does because really the distribution of the study effects in the two-step method, so like in the first stage, that depends on the number of participants in those trials, so not the number of studies. And in the second step, if we're thinking of the random effects distribution, well, we assume normality typically, but we don't really know. But that's the same whether we did a one stage or a two stage, that we'd have that same assumption. So I don't think it matters.
Thank you. Oh gosh, lots of lots of questions pouring in by the. Oh no, those are all thank yous. So I don't know whether anyone else has got any questions or anything you want to add, Andy.
Uh, oh, just big thanks, like you, Tom, to Richard. I thought that was fantastic, and I haven't laughed as much in a talk for a long time, Richard. Actually, I really enjoyed the football bit
Oh,
as well.
as long as it was at the appropriate bits to laugh.
Well, yeah, yeah, that's what I always worry about in my talks. I'll just very briefly, if it's okay, in a recent meeting that me and Tom had with some of the wider team, there was quite a heated debate, I think it's fair to say, Tom, on the potential use of AI to support some of this sort of work across thinking about the prime IPD steps, particularly relating to the processing, and whether you've got any thoughts on whether that is something that could come in over time. Just I suppose, methods in general that might make the process more efficient.
Well, never say never, and I think that these things will come in and can be helpful in some ways. My worry is that they will actually lead to problems because there is so much nuance for each data set. I mentioned about the back and forth with the original study authors to understand their data better, to check that data, to rectify errors, to make sure it aligns with study publications and so forth. That I just think it needs that personal touch, and I think having some automated AI approach to do it is problematic. Maybe where it might come in better is in terms of searching for studies, searching for relevant studies. Maybe that's where it can come in to help screen, um, particularly in areas away from trials, such as prognosis studies, which are poorly defined a lot of the times. Maybe it could help with some sort of full text screening quickly. But we'll see. Never say never, but I'd be very cautious right at the moment.
Yeah, I think that's probably the where we landed collectively, Tom, isn't it? I think it was interesting discussion, but yeah.
Great. Um, so I think that's all the questions covered. So thank you very much. Thank you to our hosts at Yorkshire and Humber Art. Thank you, Divine, for organising the
Yeah,
seminar.
thank you so much.
Thank you, everyone. Thank you.
Thank you.
Thank you, Divine. Thank you.
Thanks, guys.
Cheers.